Good morning. Welcome to Transfer Phenomena in Bioprocess Engineering Week 4 session. So today we will discuss about a pump in Bioprocess Engineering. So what is the pumps here? So normally pump is a mechanical device. It's used to transport the liquid, then the slurry, sometimes some gases from one location to another location. It does not create energy. It transfers only mechanical energy from the driving motor to the fluid section. So there is a three types of energies here. The transferred energy increases the total mechanical energy of the fluid in the form of, the first one is the pressure energy. So there is to move the fluid from low pressure to high pressure. So that's called the pressure energy here. So kinetic energy is to increase the fluid flow rate, that's increasing velocity. Normally we always kinetic energy we write of mv square. So we want to increase the velocity, we will use for kinetic energy here. The pressure energy, the P. The potential energy here normally is we called as a mgh, that's the potential energy. So here based on the lift the fluid from lower elevation to higher elevation, there is a high difference. From high difference, this energy involves here. So that's called a potential energy. So these are three types of energy. We already discussed the Bernoulli equation. That is the first one is the P rho by M. So that is the pressure. Then of me square, that is a kinetic energy. Then mgh is the potential energy. So three types of energy together, adding that one, then what is how much amount of Q then plus W. That's the famous Bernoulli equations are there. From there only we derive this one. Okay. So normally the transfer of energy increases to the total mechanical energy of the fluid in the form of these three types of energy: pressure energy, kinetic energy, then potential energy. So what is the importance of bioprocess engineering pumps? So you want to transfer the culture media from one place to other place, then the fermentation broth, then process water, then cleaning your solutions. You want to say example bioreactor, and then you want to clean the reactor, or sometimes the membrane process, you want to backwashing. So many places whatever here the bioreactor whatever, so definitely we need thorough knowledge of the pumps. Then the facilitates to sterile processing, and we want to minimize the risk of contamination. There also we will use a pump here. The supports of efficient operation, the bioreactor, especially downstream processing units, and how to utilize the system. These are places very important for the bioprocess engineering. So what are the different type of pumps so far we are using here? So one is the positive displacement pump. The positive displacement comes a reciprocating pump, then diaphragm pump, piston. So then again rotary. There is a peristaltic, gear, rotary. So different type of pumps are there, but we are going to discuss only the bolded here. One is the diaphragm pump, other one is for peristatic pump. So other classify is the dynamic pressure pump. One is the positive displacement pump, the dynamic pressure pump. There is a centrifugal pump, then propeller, then turbine. But we are going to discuss only centrifugal pump here. What are the bolded that we are going to discuss in the class today? So peristatic pump, then diaphragm pump here. So there is a two classification here. One is a positive displacement pump, another is a dynamic pressure pump. The positive displacement pump, what are working principle? How it's a working here? The working principle here. So basically the fluid is trapped inside the closed chamber. The chamber is there inside closed chamber. The fluid is trapped and moving here. The chamber volume changes due to the movement of piston and diaphragm, gear or roller. From there the chamber volume changes due to the movement of all this one. The trapped fluid is displaced from the suction side to the discharge side. So each and every cycle delivers nearly constant volume of liquid. Say example the flow rate, everything they will maintain the constant, try to maintain a constant each and every cycle if you measure that one. So what are the characteristics here? It's a constant flow rate Of course, you have to maintain the throughout the constant volumetric flow rate or mass flow rate, whatever you want to do here, you have to maintain the throughout this process the constant flow rate. Then high discharge pressure, that is also a very important characteristic here. Self-priming, that is one more thing. Then it's only suitable for the mainly viscous fluids. For positive displacement, we will use for the viscous fluids wherever there, we will use here. Ideal for accurate for dosing and metering, this one. The first one discussed a positive pump, displacement pump. Then second one is we are going to discuss a dynamic pump. The name itself dynamic. So what is the working principle here? The rotating impeller imports kinetic energy to the fluid. So the fluid is oscillated through the radially or axially, whatever axially move or radial also move. So both sides the fluid is oscillated, not only one side one. Then the volume of diffuser is converts kinetic energy to pressure energy. We discussed already what is kinetic energy of mE square, then pressure energy, then potential energy, all types of energy discussed here. So the kinetic energy converted in terms of pressure energy. So it's a continuous fluid flow is maintained during operation. So what are the characteristics here? So one is a continuous flow and same time the smooth flow should be there. Of course, we can use for high flow rate. Always we can use the high flow rate. It's a very simple construction. It's the best suited for the low viscosity fluids. The previous one is the high viscous fluids, we can use it here. But here we can only use for the whenever the low viscosity fluids we can use here. So widely we use the industrial fluid transport. If you want to use the widely used for here the industrial transport the role. So we will discuss one by one, one different type of pump here. The first one is a peristatic pump. The peristatic pump is the device of the positive displacement pump. It's a used transfer of variety of fluids including the viscous fluids. You can see here the peristatic pump. So there is the roller is here, roller, then the tube is here. It always goes through this way. This way only the fluid transfer to the tube here. The fluid is moved by trapping a fixed volume. See here, moving here inside, trapped a fixing volume within the flexible tube. The tube is a flexible tube or flexible pipe and mechanically forcing in the downstream. Say example, all type of fluid entering here, then the squeezing, then coming out. That's a way this one. The flexible tube is placed inside the circular pump, with the casing, which is compressed by the rotating roller. This is a roller, it's a rotating. It's a rotating roller, it's a continuously, it's a rotating rollers attached to the rotor. Then it's a pumping the fluids from here to here. It eliminates the risk of contamination. Why? Because we use the fluid is not exposed to the outside the atmosphere. You just entered here, it never exposed the outside. It's only inside the place only, not outside the atmosphere. So it's not exposing outside. So there is no backflow of the fluids. There is no only the forward. There is no backflow here. So there's a peristatic pump. So how the peristatic pump works here? The working principle of peristatic pump is like same human digestive system. It follows the mechanism of peristalsis, which causes the compression, then relaxation of the flexible tube through the rotary motion. So here it's a compression, then relaxation. Both sides is happening. So that's the way the fluid is transferring from one place to another place. The part of the tube under compression is squeezed, then forcing the fluid to move through the tube. Same if the rollers moves away, the flexible tube expand back to the normal open shape, creating the vacuum, then again draw the here fresh fluid. So it goes start from here, then it goes to squeeze and then expansion, then this way. It's a continuous process. It's a one side, is not the backflow here. So next, what are the type of peristatic pump here? Only the hose pump. It's used for heavy duty. Normally the hose pump we use for heavy duty. It's a reinforced tubes called hoses to handle a high mechanical stress. The stress is a high mechanical stress. but it works under high pressure up to 10 bars. So high pressure, from high pressure always we can use for the 10 bars. The pump casing is filled with a cooling lubricant, minimize the friction and the heat generation. That's a additional point of the type of hose pump here. It's always used for that industrial transport, because whenever if you have high pressure, we can always use industrial transport, because where there we'll handle a more amount of the liquids here. So like viscous chemical slurries, then sewage and sludges, wherever there we can use the hose pump. That's one of the type of peristatic pump here. Another type of peristatic pump is the tube pump. So the tube pumps works up to 5 bars. The previous one is the hose pump, that's work for 10 bar. This up to 5 bar we can work here. It's a low pressure condition. It's a lightweight, the flexible tubing here. So it has a multiple rollers. Inside the multiple rollers are there. That's say example 228 to compress the tube here. It's mostly used the laboratory scale and reactor for nutrient dosing, acid base pH control, then the fluid sampling. All the places we will use for tube pump here. So another is a 360 degree eccentric pump. That is another type of peristatic pump here. It's a traditional pumps using the multiple roller. So this pump utilizes the single then larger eccentric rolled mount inside the casing. So the flexible tube is compressed over a full 360 degree, the rotation base, rotation. So definitely this increasing the tube is compressed only one bus per cycle. One complete cycle, it's increase then decrease here. So definitely this is a highly effective handling for ultra viscous fluids, then downstream biopharmaceutical purification lines requiring for stable then pulse pre-delivery here. So the peristatic pump, what are the factors responsible for the tube selection? Another point. It should be a chemical compatibility, of course pressure, then temperature or tolerance, these are well controlled here. Then gas permeability, that's a very important, that's a transparency. Then the other cost wise also should be a low cost or high cost, but it should be a low cost, that only we can use here. So what are tube material for peristatic pump here? Normally we use a silicon, so widely used in the laboratory application. Sometimes we will use for the neoprene, useful for the abrasive liquids. Then another one is a morphine. It's made of thermoplastic material. It has a wide chemical compatibility. It blocks the visible and ultraviolet rays. These are different type of tube we are using here. Silicon, neoprene, then morphine. So far we discussed then what are the advantage of our peristatic pump here. So it's a contamination of fluid transfer. It's a very gentle to handle, especially shear sensitive fluids. Of course, it's a self-framing, it can run dry also. It is suitable for sterile operation, and then corrosive fluids also we can use here. It's excellent for accurate dosing and metering here. So only the tube will contact the fluids, not in the outside of, only the tube is the contactive fluids. So what are the limitation here? It's only works some limited flow rate and limited pressure. So the tubing sometimes wears out, sometimes we want to require the replacement. Then sometimes will come as a pulsating flow. Then limited by tubing material compatibility. Of course, the operating cost due to the, if you want a tube replacement, the operating cost goes very high. But at the end of the day, the lower efficiency than the centrifugal pump. If compared to centrifugal pump, the efficiency here lower. So next is a diaphragm pump. So what is the diaphragm pump here? That's it's a reciprocating pump. It's a reciprocating pump here. It draws the fluid in the pump and releases through the check valves by means of flexile diaphragm. So then oscillate between the increasing and decreasing the volume of pumping chamber. It's increase and decrease from the pumping chamber. So what are the main components here? The diaphragm pump here, the flexible here, rubber, then PTFE, then elastomer. Then pump chamber section of inlet check valves, it's always discharge the outlet check valve. Connecting rod is here, then shaft, crankshaft, we call it crankshaft here, or pneumatic actuator, or suction and discharge ports also there. These are different main components for the diaphragm pump here. So, how the working principle diaphragm pump here? So, one is the suction stroke, the first point number. So, what happened the first one? The diaphragm move forward. See here is moving forward, the diaphragm move forward. Then the chamber volume get increases. The chamber volume here gets increases because moving forward, the volume gets increases. So, once the volume get increases, automatically the pressure inside the chamber get decreases. The pressure chamber get decrease inside here. So, once get decreases the below the inlet pressure, then automatically the inlet valves open here. The inlet valves open here, but the outlet valves remains closed. So, now what happened? The liquid enters the chamber, pump chamber. So, what is this one? First one is the diaphragm, the pump moves backward, it is moving backward here. Then the chamber volume get increases because the volume get increases. Once volume increases, the pressure decrease. Once it gets pressure decreases, automatically the inlet valve open, then outlet valve remain closed, the fluid is entering this side. So, this is a suction stroke, the first point. The second one is for discharge stroke. So, there is a diaphragm move again forward, moves forward here. Once you move, then automatically the volume get decreases. See the here volume increases and here volume gets decreases here. So, once volume get decreases, the pressure inside the chamber gets increases. So, once increases, automatically the inlet valve gets closed, then outlet valve should open, outlet valve open here. So, then liquid discharge the pump. This is a way the diaphragm pump is working. The two mode is, one is the discharge stroke, another one is the suction stroke. Two mode is working here. So, what are the advantages and disadvantages of a diaphragm pump here? It's a leak free contamination and this is a free operation, and of course, this is self priming. You can use for the self priming here. It's handle the corrosive and viscous fluids here. It is a suitable for the shear sensitive fluids. It's always very suitable for the shear sensitive fluids here. It's accurate dosing, then the metering here. It can handle again slurries and some suspended solids, some wastewater treatment process, always we can use here. So, what are limitation again here? It's a low flow rate and the pulsating flow. The flow rate is low. Then diaphragm requires periodic replacement. We have to replace the periodically, that one. It's not suitable for the very high flow rate application. Of course, it's a lower efficiency than the centrifugal pump. What is centrifugal pump we are using now compared to that one? It's a lower efficiency here. But higher maintenance due to the diaphragm is moving forward and reverse. So, the maintenance cost sometime will go higher also here. These are the limitations for this pump. So, next is centrifugal pump. We discussed the different type of pumps. Then finally, now centrifugal pumps. The centrifugal pump, what happened here? It converts rotating the mechanical energy from a motor to kinetic energy. Is coming as a kinetic energy is of mv square, because whenever velocity gets increased, and that we always call as a kinetic energy. So, which is subsequently converted into pressure energy. So, this is finally converted as a pressure energy. Okay. So, what are the working principle here? The first, the fluid is entering here, the fluid enters the pump through the suction inlet, reach the impellers. So, this is a way here, release entering here, so reach the impeller here. The acceleration here, then impeller start rotates with a high speed, at high speed, then imparting kinetic energy, because when you increase the speed, then velocity also get increased. So, there is a kinetic energy is there. The kinetic energy to liquid, then throwing it radially outward by the centrifugal action. So, then kinetic energy get increased, this convert to kinetic energy to pressure energy. So, the pressure discharge here, the high velocity of liquid enters here, where the flow area gradually increases. So then the velocity get reduced, is converting completely in terms of kinetic energy to pressure energy. So what is the fluid discharge here? The pressurized liquid exits through the discharge outlet delivered to the record system. So finally the fluid getting discharged here. That's the overhead here, we can see here. So through delivery valve. So this is a way entering and through rotor, and again finally so moving to the delivery fluid discharge. So what are the part of centrifugal pump? So one is the impeller. So impeller centrally is located, it's a revolving disc. The impeller is centrally located, the revolving disc here, and the curved blades. Impeller can be classified according to the design. We can't call as a open or sometimes semi-open or closed impeller. But the impeller design influences the pump efficiency than the performance, because the impeller is a main to decide the efficiency of pump here. Then casing here, it can also be referred to as a volute. The outer coating encloses the impeller and control the fluid flow. The pump efficiency influenced by the casing design also. The design feature modifications such as single volute or double or diffuser casing, we can always this one do. Then suction and discharge ports here. The suction part where the fluid enters the pump, then when the discharge is where the fluid escape leaves here. That's called as a discharge ports. So two type of ports here. One is the suction ports, then discharge ports here. There is a shaft is there. There is a crank shaft. The shaft always connect the impeller to the motor to transferring the rotational energy. It's a continuous rotation. It's a rotational energy. It must be long lasting and correctly adjusted through the avoid problem like vibration and misalignment. So there is a seal and bearings are there. There is a mechanical seals, because there is a leaking will be there. So the mechanical seals prevent the fluid leaking along with the shaft. So ensuring the pump's integrity here. So what are the advantage of this centrifugal pump? Because we discussed centrifugal pump, what are the advantages then limitation here? It's a very simple and compact construction. It's a smooth and very continuous flow we can use. It's a higher flow rate and we can use with the low maintenance. It's suitable for large volume of liquid transfer. Sometimes if you want a large amount of volume of liquid you want to transfer, the centrifugal pump is the best one. It's a low operating and maintenance cost. It's a very easy to install and the operation here. But what are the limitation? It's a not self-priming. So whenever high viscous fluids, then the performance is a very okay, give poor performance. So we have to see whether it's highly viscous or low viscous liquids are here. Sometimes the flow rate varies with the system head. The head of the system automatically varies with the flow rate also. Sometimes then the cavitation susceptible to be a cavitation also. It not suitable for accurate metering and dosing. So wherever the low flow rate if you use, the efficiency get lower efficiency and especially low flow rate. But if you want high flow rate, it gives a very good efficiency of this one. So far we discussed all the three type of pumps. Now we will discuss the centrifugal pumps, how this works here. So there is a volumetric flow rate, volumetric flow rate, the 2 pi r1 p1 v1 is a normal velocity. So volumetric flow rate is a meter cube per second. It's a meter cube per second, the unit here, and this is the area meter square, then velocity meter per second. So finally we get a both side meter cube per second. That's a volumetric flow rate. So volumetric flow rate point 1, we have assumed two locations, this one 2 points. So other one is for point 2, the 2 pi r2 same area, then b2, the v2 is the normal velocity. So assume both are equal, then from there we can get the v2n at point normal velocity at 2 equal to v1n r1 b1 r2 b2. If r2 b2 this value is high compared to this one, then definitely the velocity get decrease. But reverse way, and the r1 b1 increase, then automatically this also get increase. It's a normal this one. So now torque, centrifugal pump, how this, okay, create the torque here. The motor supplies torque to the impeller, but the pump performance depend on the how much of the mechanical energy transferred to the fluid. So the famous Euler equation is there. Euler equation, it's always discussed that one. The T shaft torque, we call it as a shaft torque into rho into V, rho V, then R to V2, V2 is the velocity. So T is the tangential velocity at 0.1 and R1 V2 is the 0.2. So then alternative we can write for tangential velocity Vt equal to V sin alpha. So replace here V sin alpha. So then we will get the shaft torque here, this modified equation here. So same the centrifugal pump, if you assume efficiency 1, pump efficiency 1, normally it's not there, but assume efficiency 1, then the brake horsepower here omega T shaft. But we know already what is the T shaft here. So then the omega here, then we get the Euler equation here. But finally the head of that one head here, H equal to, after modification we can write 1 by G of this one. So very standard derivation. Then hydraulic power W equal to rho G V VH here, that is the head is head. So again equating, already we know what is the power here, then equate that one, both if we equate, then finally we get the head of that one, cancel all common terms, then we will get this equation. This is for only you can use for centrifugal pump. So again the same way we are trying to more discussion of this one. So for V2 square equal to, in terms of V2 square, we can write outward velocity triangle V2 square plus VR2 square in terms of cos beta 2, but the V2 relative, this one is substitute, then you modify, then we will get the beautiful expression of VR2, velocity of that one, the triangle here we will get here. So after solving again this one, then we get a height of using inlet and outward velocity of triangle, then we will get finally h of head of that one equal to, we can express this way. So this is a very famous equation, I already discussed. This is a pressure energy P by rho G. P by rho G is a pressure energy. The another one is a kinetic energy. This is a kinetic energy. We discussed, it's a Bernoulli equation. Already we discussed the Bernoulli in previous class. And then there is a steady state. If it's unsteady state, then we have to add here, like in terms of velocity, all this one. So always we assume as a steady flow energy equation. And here this is a potential energy. So three type of energy involved here. So that is one is a potential energy, then it's a kinetic energy, and it's a pressure energy, the P by rho G. So comparing the net head equation, we can take always this one. So after solving this one, we get the maximum get V1 of t equal to 0, then automatically this get 0, then we will get the VR1 equal to V1 by tan beta 1. So V dot equal to this equation, finally the Stokes entry for the condition here. So we will discuss one problems. So there is a centrifugal pump, it's rotating 1500 RPM. So if in terms of omega, we can say radian per second, and air enters to the alpha 1 0, then 35 angle alpha 2, then there is a inner radius R1, then there is a blade width is B1 is a 5 centimeter, the radius also this one, then outer radius is R2 10 centimeter, then there is outlet blade width is there, the volumetric flow rate is 0.18 meter cube per second, assume the efficiency of pump equal to 100. So calculate the net head produced by the, in terms of water column height, then also calculate the required the brake horsepower BHP in terms of watts. It's a very simple problem. So these are already given problems here, the radius or outer radius, inner radius, then blade or volumetric flow rate, density, pump efficiency. So what is the brake horsepower here? So VR1 equal to omega R1, omega value we already know that one, substitute and get a VR1, same way for VR2. velocity of the blade speeds here. Then calculate the normal velocity, the V1n. We already know the equation. From that equation we calculate V1n normal velocity. First case the alpha 1 is 0, the second case is 35, I think 35 here, the angle is 35 degree, alpha 2. So, the first case is the alpha 1 equal to 0. So, then this case the V1t equal to 0. So, now calculate the outlet of normal velocity V2 here. So, we know the value of V1n, then all values we know, we can get the normal velocity of V2 here. So, the V2 equal to 13.99 meter per second. For calculate this one absolute velocity here. For outlet of tangential velocity V2t here 8.03 meter per second, because alpha equal to 35 degree alpha there one. So, the head equation already we know that one, we discussed the equation, the h equal to 1 by g of this one. Since the V1t 0, then we get the head of this one in terms of air. Now, we have to convert in terms of liquid. We got only in terms of air, we have to convert in terms of liquid. So, liquid we know delta P equal to rho g h, the pressure rise in the water column. So, first get the delta P. So, once the delta P you know rho and g h value. So, all values just substitute here, then we get the delta pressure here, but now in terms of water height you have to convert water height here, same value, but the rho is the 1000 because density of water is 1000. So, in the water we get a 15.4 meter of water, the head of that one. So, then break horsepower here we got same value, the rho g v this one. This is a volumetric fluid. See the volumetric fluid is the V dot is a volumetric fluid. Density is there, g is there, just substitute, then get the value of brake horsepower. But they asked what is the brake horsepower bhp, then what is the water height, the equivalent that one, equivalent of water height, the problem. So, the comparison of now, this is a final comparison, what is the difference between centrifugal pump, then diaphragm pump, peristaltic pump. So, these are a different type of pump type we already discussed, one is the dynamic and positive displacement both side. So, it works with the impeller centrifugal pump, it works with the diaphragm and this work with the rollers. So, smooth and pulsating flow and nearly slight pulsation here, high flow rate, low, then low to moderate. Pressure of course, this is a moderate, then high, then moderate here. These are different type of pumps in the comparison. So, especially application we will see the contamination risk also here moderate only, but very low, extremely low. But here we will always use the fermentation process circulation, cooling water system. But here the diaphragm pump always use the chemical dosing, then slurry pumping, wastewater treatment here. But a peristaltic pump we will use for cell culture transfer, then media feeding, enzyme and blood handling, pharmaceutical dosing, sterile bioprocessing, mostly used for peristatic pump here. So, what are the major advantage here and then limitation here? It's a high flow rate, of course, this all we will use for low flow rate sometime. But the major limitation here, it's a cavitation, poor viscous fluids here, but we can handle the pulsating flow and here also tubing here and limited flow rate here. So, these are different type of centrifugal pump and diaphragm pump, then peristatic pump. So, most of the cell culture, all this process we are using the peristatic pumps here. Thank you.